Welcome to my video course on Communications-Based Train Control, CBTC. I'm absolutely thrilled to be your guide today. There's this incredible technology silently revolutionizing modern railways right under our feet. And today, we're going to unpack exactly how the whole shebang functions to keep our cities moving safely and efficiently. Let's get right into it. Okay, so picture this. For decades, conventional railways relied on what we call fixed block signaling. It's basically like taking a track and dividing it up into static, unchangeable chunks. And to keep trains from hitting each other, you had to leave massive, completely empty spaces, entire empty blocks between trains going the same way. But as our cities exploded in size, we desperately needed more capacity. Enter CBTC. It's a total game changer. By shifting to a dynamic, radio-based network, we can pinpoint a train's exact location in real time. What does that mean for us? It means we can safely shrink the distance, the headway between trains. We run trains more frequently, squeeze every ounce of capacity out of the tracks, and most importantly, totally eliminate collisions. Pretty amazing, right? So, here's our roadmap for today. 1. Introduction to CBTC. 2. The Trainborne subsystem. 3. The Wayside subsystem. 4. The OCC subsystem. And finally, 5. The data communication system. Think of the overall architecture as our master blueprint. We've basically got 3 major functional blocks working together: the Wayside system, the Trainborne system, and sitting right at the top, the ATS or OCC system. Now, the crucial thing here is that none of these work in isolation. They're constantly talking to each other through these physical and functional interfaces. And all of this chatter is handled by the data communication system sitting right in the middle. Truly, if you can grasp how these blocks interact, you've unlocked the real secret to modern rail safety.
All right, Section 1, Introduction to CBTC, Core Concepts.
So what actually is CBTC at its core? Well, unlike those older, clunky systems, CBTC gives us high-precision train location tracking that is completely independent of traditional track circuits. It relies entirely on this continuous, high-speed, two-way communication between the train and the wayside. And why do we do all this real-time data exchange? Simple: absolute safety. We're talking about utterly eliminating collisions and literally preventing any train from physically going over its speed limit.
Moving right along, Section 2, the Trainborne subsystem, onboard reflexes.
Okay, so right on board the train, we've got 2 absolutely vital systems you need to know about. First up is ATP, Automatic Train Protection. Think of ATP as your ultimate safety net. It's constantly keeping an eye on the train's speed, making sure it stays within the limits, and it'll instantly slam on the brakes if it has to. Then we have ATO, Automatic Train Operation. While ATP is keeping you safe, ATO is doing the actual driving. It's the system that handles the smooth acceleration, braking perfectly at stations, and even opening and closing the doors. Now, where does this ATO technology actually lead us? Guys, we're not just talking about cruise control for trains here. At its highest level, this tech allows for fully automated transit. I mean, we are talking about trains literally driving themselves with absolutely 0 human operators on board. No way, right? The ATO manages everything: the driving, the safety checks, the doors, all on its own. And of course, you've got that ATP system always running in the background just to guarantee everything is totally safe.
To make all this magic actually happen, the train uses some very specific hardware. The real brain of the operation inside the train is the carborne controller, or CC, which is just constantly crunching numbers on the train status. There's also the train operator display, the TOD, which provides an interface if a human is supervising things. And then, right underneath the train, you've got the tag reader systems and antennas. As the train zips down the line, these antennas are actually reading transponder tags stuck right on the tracks. This confirms the train's exact physical location down to the literal centimeter. How cool is that?
Next up, Section 3, the Wayside subsystem, Local Zone Management.
Now, a railway network is obviously massive, right? So to keep things manageable, it's chopped up into multiple, totally independent zones. And each of these zones has its very own boss, the zone controller, or ZC. The ZC is keeping track of every single train in its territory and calculating exactly how far they can safely move. Alongside the ZC, we've got those transponder tags on the tracks we just talked about, plus interfaces with the vital interlocking systems. But here's the really brilliant part: the compartmentalization. Because every zone has its own independent infrastructure, the system's reliability goes through the roof. If one zone suddenly has a hiccup, it doesn't take down the whole city's transit network. It just makes sense.
All right, moving on to Section 4, the OCC subsystem, the global brain. I mean, just look at the massive scale of an OCC. This room basically has a god's eye view over the entire railway network. This is where the automatic train supervision, the ATS system, actually lives. So while the train is busy protecting itself and the Wayside is handling the local traffic, the ATS is there to make sure the big picture actually makes sense. It's making sure the daily schedule stays on track, it's routing trains, and it can even dynamically adjust speeds and permissions across the whole network. It's the ultimate conductor, keeping everything running like absolute clockwork.
And finally, Section 5, the Data Communication System, the Invisible Network.
So, the Data Communication System, or DCS, is essentially a broadband network. But guys, since we're dealing with heavy machinery and human lives here, this can't just be your standard home Wi-Fi setup. Absolutely not. It's built on a strict rule. Vital traffic must have redundancy at literally every single level. The core network, the Wayside network, those train to Wayside wireless links, they are all totally duplicated. That means we always have two completely distinct, two-way paths for data to travel. If a router completely fries or a signal drops, it doesn't matter. The vital data still gets exactly where it needs to go instantly through that backup path.
Okay, let's tie this all together. Think about how these pillars align with each other. The Trainborne subsystem, that's basically the reflexes in the eyes of the operation, using the Carborne controller and antennas to handle driving and immediate safety. Then you've got the Wayside subsystem, acting like our local traffic cop, using zone controllers to manage specific chunks of track. And hovering above it all is the OCC, the global brain, using ATS workstations to handle the high-level scheduling and routing. And remember, all of these pieces are just constantly chatting with each other over that bulletproof data communication system.
So by mastering these three architectural pillars and securely networking them together, we've managed to jump from those fixed, inefficient blocks of the past right into the dynamic, highly fluid railways of tomorrow. It definitely leaves you with an exciting question to ponder. As this tech gets even sharper and more precise, what is the ultimate limit for the future of fully autonomous public transit? Thanks, we can see in next video.